we are going to start with Hans Christian Ørsted. Now, Ørsted discovered that moving electric charges, or currents, can create magnetic fields. In 1819, he placed a compass near a wire, and he could tell by the direction that the needle in the compass was pointing that electric current was flowing. So, to give you an example of this, I'm going to give you a clip of his experiment.
In 1820, the Danish chemist and physicist Hans Christian Ørsted performed a celebrated experiment demonstrating that an electric current passing through a wire could deflect a magnetic needle. The experiment can be reproduced by means of the following apparatus. A wooden base carries a magnetic compass. A brass frame above the compass holds a thick copper wire with a small clip at each end. A pinion is used to raise and lower the wire above the compass needle to determine the relationship between its deflection and its distance from the wire, through which an electric current flows. 3 levelling screws ensure that the system is perfectly horizontal. After arranging the device so that the magnetic needle is parallel to the conducting wire, the 2 ends of the wire are connected to the electrodes of an array of batteries, and a current is sent through it. We observe that the needle deflects towards a position at a right angle to the direction of the wire. When the direction of the current flow is reversed, the needle still tends to deflect toward a perpendicular position relative to the wire, but this time its poles are reversed from the previous position. In a similar experiment, Ørsted demonstrated that a continuous electrical current flowing through a conductor generates a magnetic field. He was thus the first to prove the interdependence of electricity and magnetism.
All right, next we're going to talk about Michael Faraday. He's the one that discovered electromagnetic induction. Electromagnetic induction is the basic principle behind electric transformers and generators. And pretty much what he figured out is that if you move or change the magnetic field, it can create an electrical current. And then there is a law that came up after Faraday, and Faraday's law states that the current in a coil is proportional to the rate at which a changing magnetic field is passing through the coil. To help show you guys this, here is a clip about Michael Faraday.
Hi gang, this is the Faraday motor. It's a fun, simple experiment you can do using household parts. It was the very first electric motor ever made and was demonstrated by Michael Faraday in 1821. And we're all set to go. Take the battery, hook one end to one end of the battery, connect the other end to the other end of the battery. Whoops. So it'll hold. And there you can see it's working. Here's how it works. The battery makes electrons flow through the circuit. In the glass, the electrons move from the copper wire that's hanging down and free to move through the salty water to the aluminum foil. That causes electrons to flow along the wire.
Next, we have Heinrich Lenz. Heinrich Lenz formulated the Lenz law, and his law helps us to understand and how to utilize how electromagnetic circuits react to Newton's third law and the conservation of energy. His law states that if an induced current is flowing, its direction will always be such that it will oppose the change in which produced it. Here is a clip about Heinrich Lenz.
Today I wanted to demonstrate a sciencey type effect that I find pretty cool, which is based on the concept of electromagnetic induction. So let's get right to it. Now what I have here is a copper pipe and a very strong neodymium magnet. The magnet right now is wrapped in electrical tape because I learned very quickly that if you let 2 of these get too close together, they will definitely attract one another and slam together with a force such that they will begin to break pieces off of one another if they do it too many times. So the tape just serves to sort of soften the blow if either one of them wander too close to the other. Now copper is an electrically conductive metal, which just means that it facilitates the flowage of electricity, but it is definitely not magnetic. See? But something very interesting does happen when you drop the magnet through the pipe. However, I do need to preface this demonstration by telling you this is just a regular copper pipe I got from Home Depot. This is just a regular neodymium magnet I got off of Amazon. There is no tomfoolery, shenanigans, or wizardry involved. It's just science. Alright, check it. Here we go. Magnet pipe. What? One more time. Okay, from the top. Again, there was no tomfoolery involved. It's just science. Also, I like saying tomfoolery. So now on to the explanation as to why the magnet falls so slowly through the pipe when neither one of them seems to be attracted to the other. The reason for this seemingly strange behavior was discovered in 1835 by a Russian physicist named Heinrich Lenz. Lenz's law says that an electric current induced by a changing magnetic field will flow such that it creates its own magnetic field that opposes the magnetic field that created it. Duh. So in terms of the pipe magnet demonstration, what's happening here is that as the magnet moves through the pipe, it induces an electric current in the copper that moves through it. That electric current itself generates a magnetic field that opposes the magnet as it falls. And if that doesn't make much sense to you, then don't worry, you're in good company. Magnetism in general is a crazy quantum mechanical effect that's been magnified so that we humans can perceive it on a macroscopic scale, but it does make for some pretty good demonstrations, I think.
Finally, we have James Maxwell. Maxwell actually put Faraday's law into a mathematical form. While doing that, he developed 4 different equations that unify both electricity and magnetism together. He was also able to explain magnetism in terms of a field instead of just the force lines. And we'll be looking at the difference between fields and force lines later. Here's a clip about James Maxwell.
James Clerk Maxwell was a Scottish physicist and mathematician who helped shape our understanding of the modern scientific world. Maxwell was born as John Clark in Edinburgh to a wealthy and aristocratic family. He was homeschooled until the age of 8, and he was then sent to the prestigious Edinburgh Academy after his mother died. He wrote and presented his first scientific paper to the Royal Society of Edinburgh when he was just 14 years old, but his paper was rejected as he was believed to have been too young to have written the paper himself. At the age of 16, Maxwell attended classes at the University of Edinburgh, and at 18 he presented 2 more papers to the Royal Society, but was again deemed too young to have written the paper, so it was presented by his tutor at the time. He then moved to Cambridge University in 1850 and graduated with a degree in mathematics, then moved to Aberdeen University where he formulated a theory on the 200-year-old question on Saturn's rings, and how they remain stable without breaking up or crashing into the planet's surface. The young Maxwell solved the mystery, and his theories were confirmed by the Voyager space shuttle over 100 years later. Maxwell then moved to King's College London, where he produced the world's first colour photograph and experimented with electromagnetism. Through this work, Maxwell laid the foundations for the modern applications of television, radio, radar and microwaves, as well as infrared technologies. He worked on telescopes and thermodynamic theories, and developed many mathematical equations and theories that explained and summarized mathematical thinking at the time, which laid the foundation work for Albert Einstein's special theory of relativity, as well as the quantum theory made famous by Max Planck. Maxwell died at the age of 48, but his contributions to science are considered to be equal to those of Einstein and Isaac Newton. In the Millennium Survey of the greatest physicists of all time,